In order to automate the fish counting process in the fish farming industry, we propose a new synthetic data generation platform utilizing our new biology-inspired fish simulation, Foids. Fish farming is an indispensable part of sustainable food production. However, because it takes place in an underwater environment, most terrestrial technologies cannot be used, and industry IT adoption lags. It is important to know the number of fish when feeding them. Currently, fish are counted by eye when they are released into the water after being scooped up in nets. This method is stressful for the fish, and the count is not particularly accurate. To solve this problem, we propose a method to automate the counting of fish using computer vision. When creating a training dataset from videos of fish, the manual labeling workload takes an unreasonable amount of time and effort. Even if you did manually annotate fish bounding boxes, the fish are often overlapping, making labeling difficult. Fish and shadows can be hard to distinguish. Low resolution can make fish hard to see, and bright lights can partially obscure fish. What's more, the data you've worked so hard to label is only a fraction of the data required for computer vision training. In order to fully train robust and accurate computer vision models, a large training dataset containing many variations in weather, time, location, water clarity, fish species, and number of fish is required. Before labeling can even begin, it is necessary to obtain this base video data. We solve this issue by automating the generation of synthetic data with annotations using computer graphics. In order to achieve this, a realistic simulation is needed. By simulating realistic fish behavior and their environment via computer graphics, the world and screen position of each fish are easily obtained and can be used to generate 2D and 3D bounding boxes. Silhouette ground truth data can also be produced. By parameterizing the date, time, weather, water clarity, water temperature, light intensity, number and species of fish, fish size, and fish speed, and programmatically varying the parameters, a large number of patterns of data can be automatically generated. 2D bounding box ground truth data, 3D bounding box ground truth data, and silhouettes can be obtained automatically. By training a deep neural network based on YOLO v4 with the generated scene images and 2D bounding box data, a robust and accurate region proposal model is achieved for our fish counting application. To make our synthetic fish farm as realistic as possible, we collected data from a real fish farm. We obtained data from salmonids and created 3D models. We collected latitude and longitude, underwater temperature, light intensity, and underwater video data. We modeled the fish cage in 3D. We recorded footage from the edges of the cage at a depth of 4 meters and from the center of the cage at a depth of 6 meters. Here is the captured video and complete view of our simulation. The video data we recorded was taken from around 11 a.m. to 12 p.m. But using our proposed method, by reproducing the light from the sun based on its position in the sky over time, it is possible to generate data with our simulation that is not in the recorded data. Individual fish motion comprises 12 animations based on behavior observed in the recorded data. Animation playback is controlled by a finite state machine. During transitions between states, animations are blended, resulting in smooth motion. To produce the schooling behavior inside the cage, we designed an algorithm based on fish biology and ecology and named it Foids. Fish's temperature preferences differ by age and per individual. As the water temperature changes, fish swim to different depths to find their preferred temperature. Just like temperature, there are individual and age differences in fish light intensity preferences. As the light intensity changes, fish swim up and down in pursuit of their preferred light intensity. We added a biologically based rule to handle collision avoidance with walls. When a fish comes within 4 body lengths of a wall, it engages in avoidance behavior. The closer a fish is to the wall, the stronger the force it feels, and the more it changes its direction. Based on studies from the aquaculture literature, we set the sensing range of fish to 3 body lengths. Individual schooling behavior is affected by neighbors in this 3 body length radius. Based on a study by Oppendal et al., swimming speed is determined by the body size of the fish. The larger the fish is, the faster it can swim. We set the per fish simulation update frequency to 200 milliseconds, based on the decision-making interval time proposed by Miller. By using the Foids algorithm, we were able to achieve a realistic simulation of a school of fish in a caged environment. We used our trained computer vision model to detect and count fish in a video taken from the bottom of a fish cage. With our proposed method, a fish count can be calculated, without handling the fish, within 10 seconds. With the conventional method in a fish farm, the fish must be handled, and the count took 9 minutes and 39 seconds. The estimated count using human vision was 272, while the one using our fish counting system was 264.